everyone. My name is Marvin Borsdorf. I'm a PhD student at the Machine Listening Lab at the University of Bremen in Germany. In this presentation, I will talk about a recent work with the title GlobalPhone Mix-to-Separate out of 2, a multilingual 2000 speakers mixtures database for speech separation. This work has been carried out together with my colleague Chenglin and our supervisors Professor Dr. Haizhou and Professor Dr. Tanja Schultz. In the next 15 minutes, I will briefly introduce our motivation and talk about the design concept of a GlobalPhone MS2 database. I will show the experimental setup and provide the results and give a little discussion on them. And finally, I will conclude our study. Humans are able to focus and follow on the voice of a specific desired target speaker in a situation of multiple talkers or multiple sounds. While this so-called cocktail party problem is easy for humans, it is still an unsolved and hard task for machines. Source or speech separation describes the task which tries to emulate this ability on machines. And over time, different techniques and models, for instance, deep clustering, permutation variant training, or conv-testnet as time domain architecture, have been proposed and strongly leveraged the research in this field. On the other hand, there are several proposed databases. The Wall Street Journal 0-to-Mix database comprises speech of English speakers in 2 talker mixtures. And this is probably the most studied database in speech separation so far. The WAM database adds ambient background noise to the clean speaker mixtures of the Wall Street Journal 0-to-Mix database to better reflect real-world conditions. In WAM-R, the WAM database has been extended with reverberation to simulate an even more realistic scenario. And LibriCSS was created based on the well-known LibriSpeech corpus, while LibriSpeech itself was originally introduced for ASR purposes. The LibriMix database combines the speech data of LibriSpeech with ambient noise of WAM to create a large database of noisy speech mixtures. There are further databases and studies which investigated the robustness of speech separation systems, but all those databases and studies mostly cover a single language. We are aware of only one work which investigated speech separation for 8 different languages. However, multilingual acoustic modeling has actually a long history, and in the context of speech separation, we could design a system which is well suited for a specific language, but would like to apply it on a different language. A use case would be that we would like to design a speech separation system for a language which does not provide enough training data, and therefore we have to make use of the language resources of another language. Therefore, we believe that everyday situations call for robust speech separation systems in multi- and cross-lingual setups. In this work, we introduce a new first-of-its-kind multilingual speech separation database called GlobalPhone MS2, and GlobalPhone MS2 is the abbreviation for GlobalPhone Mix-to-Separate out of 2. The database comprises 2 speaker mixtures with 2,000 native speakers in total and covers 22 different languages. We perform extensive speech separation experiments and train mono and multilingual models and apply them on seen and unseen languages. GlobalPhone MS2 is based on the GlobalPhone 2000 speaker package, and the GlobalPhone 2000 speaker package is a subset of the well-known GlobalPhone corpus, which was originally introduced for ASR purposes. In the GlobalPhone 2000 speaker package, we have 2,000 native speakers with roughly 40 seconds of audio per speaker, and the database covers 22 different languages. If we pay attention to the figure on the right-hand side, we see that the number of speakers for each individual language is roughly in the same order, except for a couple of languages. And the same applies to the total amount of audio duration. But we can also see that for Chinese Shanghai and for Tamil, we just have a little amount of data. To create the GlobalPhone MS2 database, we simulated 2 speaker mixtures in 22 languages. The simulation for each language required to balance the size and richness of the data with computational effort. That means if we would have utilized each utterance within each language once, this would have led to a very small database. while if we would have combined each utterance with all other speakers' utterances, this would have created a combinatorial problem with enormous durations for the data simulation and for the training and evaluation of the models. Therefore, we decided to adopt the strategy which has been used to create the Wall Street Journal Zero-to-Mix database. More precisely, for the GlobalPhone MS2 database, we defined a fixed test set size of 3,000 utterances, and for the training and validation sets, we combined speaker utterances until the set sizes matched 30 and 10 hours respectively. While the speakers in the training and validation sets are the same, the test sets comprise different speakers, and this leads to an open set condition for the test scenarios. We sampled the GlobalPhone MS2 database with 8 kHz, and we simulated the database in the min version. Min version means the longer utterance was truncated to the length of the shorter one if two utterances are mixed. And we sampled the SNRs from a uniform distribution in an interval between 0 and 5 dB. To do the actual mixing, we applied the mixing scripts which were introduced with the Wall Street Journal Zero-to-Mix database. On the right-hand side, you can see a table which shows the number of speakers for each individual language, given in the number of speakers for the training and validation sets and for the test sets. And as already introduced, for Chinese Shanghai and for Tamil, we have less data compared to the other languages, and this is also indicated by the number of speakers. And because our first goal was to have a fixed set size of 3,000 utterances for the test scenarios, we didn't have enough data left for Chinese Shanghai and Tamil to match the 30 hours and 10 hours for training and validation respectively. And therefore, we have smaller data sets for training and validation for Chinese Shanghai and Tamil, just due to the lack of data. The models in our experiments were based on the conv-testnet architecture and therefore followed the time domain approach. We also incorporated the scale invariant signal to distortion ratio as training loss as well as evaluation metric, and we applied the permutation invariant training concept. We used the recently proposed asteroid toolkit to implement the data scheduling, the training procedure, and the evaluation step. We trained 6 monolingual models and selected tonal and non-tonal languages, which are widely spoken in different continents, and we tried to cover some of the major language families. This led to Chinese Mandarin, German, Hausa, Polish, and English. It is important to mention that English is not part of the GlobalPhone MS2 database, and therefore we incorporated the Wall Street Journal Zero-to-Mix database. The monolingual models were always trained on one language only, but we also trained 3 multilingual models. The first 2 models were trained on 3 languages, and we selected the languages based on the 2 best performing monolingual models, Chinese Mandarin and Portuguese, and the worst performing monolingual model, German. The first multilingual model just used 33% of the training data of each language. We did this to increase the number of languages, but to preserve the total amount of training data compared to a monolingual counterpart. The second multilingual model used 3 languages with full amount of data, and the last multilingual model used 5 languages with the full amount of data. This slide shows the results of our monolingual and multilingual models tested on seen and unseen language settings. We report the performance in terms of SI-SDR improvement, which is defined as the difference between the SI-SDR of a separated signal and the SI-SDR of the signal before the separation. We individually report the results on the languages which were also part of the training, and with eval 17, we report the mean SI-SDR improvement over the remaining 17 GlobalPhone MS2 languages. With eval all, we report the mean SI-SDR improvement over all GlobalPhone MS2 languages and the Wall Street Journal Zero-to-Mix database altogether. We can see that the monolingual GlobalPhone MS2 models perform well on seen languages, but occasionally sharply degrade on unseen languages. Sometimes we encounter a negative SISDR improvement. A negative SISDR improvement means that the separated signal is worse than the signal before the separation. We mainly attribute this to differences in speech, language, and speaker characteristics. Additionally, even if the GlobalPhone data collection followed a well-defined setup, there might be some differences between the recording sessions with respect to environmental noise artifacts or setup variations. We assume that this could also have an adversely effect since the neural network learns from the training data, especially because the encoder and decoder are data-driven and learn the latent representation from the training data characteristics. We also found that the degradation does not seem to be linked to the number of speakers, because models which have been trained on more speakers than other models do not always perform better and vice versa. The multilingual GlobalPhone MS2 models can outperform the monolingual GlobalPhone MS2 models on seen and unseen languages. This is partly given for the trilingual model with 33% amount of data and fully attained with the multilingual model trained on 5 languages. The Chinese Mandarin, German, and Portuguese 33% model shows cross-lingual performance improvements, while the total amount of training data is roughly preserved. This is easily identifiable if we have a look on the results for eval 17 and eval all. We assume that this is due to the fact that we have additional variety in speech, language, and speaker information, which are incorporated into the training step. And this would corroborate findings from other acoustic modeling studies. Our second assumption is that the multilingual training provides a broader diversity in recording sessions, and this potentially increases the robustness because, as already mentioned, the neural network learns from the training data, and if the training data covers more recording session information, this helps to increase the robustness and also helps the training of the encoder-decoder pair. Maybe at this point, a few words regarding the Wall Street Journal zero-to-mix monolingual model. This model shows a reasonable performance in general and can occasionally attain superior performance in cross-lingual settings, even if the model was trained on a different corpus. Also, the model can outperform the trilingual model on Hausa and Polish. The Wall Street Journal data was recorded in clean, homogeneous settings and comprises a slightly higher number of speakers. We suspect that this could be an explanation for the good results. Finally, we believe that an extensive multilingual training could help to form a language-independent modeling, which leads to a speech separation system which can be applied in different language settings with good performances. To sum up, we introduced GlobalPhone MS2 as a new multilingual database for speech separation, covering 22 different languages and 2,000 native speakers. We performed a series of extensive mono and multilingual experiments and tested our models on seen and unseen language settings. Our results show that multilingual models can A, improve the separation performance on almost all seen languages, and B, outperform monolingual models on unseen languages. This is mostly already attained by a trilingual model with the same size of training data. That means we have roughly the same amount of training data as for a monolingual model, but the training data comprises 3 languages instead of just 1. We attribute those gains mainly to a more comprehensive training phase that phases the model doing the training with more diverse data and recording information or characteristics, which can increase the model's robustness. Finally, we believe that multilingual training can enable new ways to increase the amount of training data. Thank you very much for your attention, and I'm looking forward to having a nice discussion with you.
Thank you for the talk. Can you hear us?
Yeah, I can hear you.
Okay, great. So are there any questions from the audience? I will then ask a question. Do you have any insight into like what properties of the languages are important to be careful about? For example, if we have a tonal language, then a tonal language should really be in the training set or something similar.
Well, this is a very important and also a hard question. Yeah, we thought about that. We did one thing. We tried to. So we had a look in the International Phonetic Alphabet for each language, and then we created like a matrix and covered all of our 22 different languages. And then we just analyzed how well those languages match each other regarding the IPA charts. And then we tried to find like matching patterns between the results and the IPA charts. But unfortunately, there were no correlations so far in our study, and this is the reason why I didn't put this in the slides. But yeah, this is actually an important thing.
Thank you. Any more questions? Okay, one last small one. You mentioned that the English model was quite better than the others and explained it with the larger number of speakers in the data set. What was the difference in the number of speakers to the other sets?
Well, the Borsdorf journal U2 mixed database has like 101 speakers in training and consolidation. And the others are roughly about like 80 or 70 speakers per language. Maybe regarding this, as I mentioned, Chinese, Shanghai and Tamil, where those data sets with just a little amount of speakers. For instance, Chinese Shanghai has just 25 speakers in the training and consolidation data set. But it's not in the table, but if we compare this, for instance, with German or with Bulgarian, the performance, if we train a speech separation system on Chinese Shanghai, the results are better compared to German and other languages. So therefore, this is one thing why we think that the number of speakers is not the most important thing.
Thanks. Yes, Reinhold?
To speculate, because you also mentioned that there were differences in the recording conditions. So if you had to make a choice, would you first match the language or would you first match the recording condition?
Well, I think I would first match the recording conditions actually to better analyze the differences in the languages, because otherwise it's hard to make sure whether the differences come from the language or from the differences in the recording sessions. So I would rather prefer well, of course, it also depends on the amount of total training data. If I have a lot of training data, and I mean, in real world conditions, we not always have like very clean situations, then it could also be beneficial to have a lot of data which simulates also a lot of different recording or environment conditions. So it's, yeah, depends, I think. Hope that answers your question.
I think it does. Any other questions? Yes, Radia?
Does it work? Okay. I have a simple question. What made you into the pre-selection of the languages in the multilingual set? I mean, what happens if I exchange one language with another?
You mean for the models we trained on, for instance, 3 languages?
Yeah, and you had 2 multilingual sets, if I'm not mistaken.
So actually what we've done is we trained first the monolingual models, and then we, from the set of, let's say, those 6 monolingual models, we just selected the 2 best performing models and the worst performing models, and then I put them together. This was actually the reason for those 3 lingual models. And for the last multilingual model, we just put all 5 multilingual models together. So this was actually the reason. Or you could also, for instance, take the 3 best performing language models, or from the entire 22 languages, you could just pick the 3 maybe best. Or you could, of course, let's say train a 22 language model, and then look what happens. Yeah, but we didn't try that so far.
Okay, thanks.
More questions from the audience? I will end with a quick one. You mentioned you did this with Asteroid Toolkit. Will the data preparation be published in Asteroid?
Maybe. We have this on the list, but didn't do that so far.
I think it could be useful for other researchers. Thank you very much. I think with this we can finish the session. Thank you all for coming, and see you at the conference.